Let's look at some Lewis structure exceptions. I'm going to start with the structure for boron trifluoride. Step 1. Determine the total number of valence electrons in the molecule. So we have a total of 24 valence electrons. Steps 2 and 3 construct our skeletal diagram. So I'm going to put my most electronegative species, fluorine, coming in at a whopping 4.0 on the Pauling scale, as the outer or ligand species. So here's my skeletal structure. Next, I'm going to disseminate remaining electrons to fulfill the octet rule. Okay. Now I'm going to do a check here. I'm going to count my total valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But boron doesn't have an octet. All right. So that means you may start trying to double bonds. What you're going to find is it doesn't work because you end up with ridiculous formal charges. So this one is going to have you scratching your head a little bit. So this is an exception. This is actually the correct structure for boron trifluoride. And yes, boron does not have a full octet. Let's look at the formal charges here. With this structure, I get zeros all the way around the structure. So this brings me to the first exception of Lewis structures, which would be incomplete octets. All right, they are rare, but they do occur. And typically we'll see these with boron, aluminum, and beryllium. But this is the most stable structure. It has an apparent violation, but it's the lowest energy, most stable configuration. Let's talk about another exception. Let's look at xenon tetrafluoride. If you determine the total number of valence electrons in this molecule, you'll have your xenon with its full octet of 8, and then you have 4 fluorines, each with 7, for a total of 36 valence electrons. Steps 2 and 3, let's look at the skeletal structure here. So xenon will go in the center, and then we're going to have 4 fluorines coming off. Fluorines are the most electronegative species. In fact, xenon doesn't have an electronegativity because it already has a full octet. All right, so if you're wondering why there's no values on your Pauling scale, that is why. Next step would be to distribute the remaining electrons around the outside. So I'll go ahead and do that now. Okay, almost done here. 2 more. There we go. And now I'm going to look at any extras and put them on the central atom. But wait a minute, the central species already has an octet. So now what I'm going to do, 2, 4, 6, 8, okay? And that's going to be all the way around, so I have 32. I need 4 more electrons in this structure, okay? And I am going to actually place them on this central species. And you might be thinking, what are you doing, Mr. Peterson? Now, all of a sudden, you're showing xenon has 12 electrons, all right? 4 more than a full octet, and that's exactly what I'm telling you. Let's look at formal charges here. 0 for the xenon, 0 for all the fluorines associated with it, all right? This is the correct structure for xenon tetrafluoride, and it is the second exception I'd like to talk to you about in this video. This is an example of an expanded octet in which the central species has more than 8 and exceeds the octet. Now, it's only possible for elements in the 3rd period and higher. The reason why is these electrons, these extra electrons, are actually placed into the d subshell, into a d orbital. And we only see the d orbital when we go beyond that, or at or beyond the 3rd energy level, okay? Because that's where the D block starts. The 3D is that first one. So for any molecules, for any structures that are in rows periods 1 and periods 2, you cannot violate the octet rule. You only have S and P orbitals for those. You do not have the D orbital, the empty D in this case, where these 4 extra electrons can be placed. Really cool. All right, the last exception I want to talk to you about, I'm going to exemplify it by doing a structure for nitrogen monoxide. So we're going to find the total number of valence electrons as 11. Then we're going to do our basic structure for nitrogen monoxide. All right, and we're going to take our remaining and distribute them. So I have 11. So you know, you might be thinking at this time, how does this even start? So 1, 2, 3, 4. Here's what you do: 2, 4, 6, 8, 10, 11. But if you do it this way, you end up with this odd electron here. And if you were to determine formal charges here, you would see it doesn't work. Furthermore, nitrogen does not have an octet. In fact, nitrogen only has 5, nowhere near 8. So this cannot be the structure. All right. So what you're going to end up doing here is you're going to move into trying a double bond. Okay. In which case you end up with this, and then you have 2 electrons here. Let's see where we're at. 2, 4, 6, 8. So oxygen's happy. Nitrogen, 2, 4, 6. All right. Now if I put 2 more here and make it 8, that means I'm exceeding my 11. 2, 4, 6, 8, 10, 12. I have 12. No, I only have 11. Okay. So what you're going to find happens here is we have an instance where, based on the formal charge, we get again a 0 if we only have, let me show you, 1 electron, if we have a free radical. So at this time, let me go ahead and do this. This is the correct structure here. Okay, 2, 4, 6, 8, 10, 11. Now let's look at octet. 2, 4, 6, 8. 2, 4, 6, but only 7. In this case here, we have a rare, unstable free radical. Now this species is very reactive, and where do you even place the free radical? You place it where it will minimize the formal charge. So in this case here, it makes no sense to place it on the oxygen, but placing it on the nitrogen gives us a formal charge of 0 for the nitrogen. And so the free radicals on the nitrogen. Now these species will often go through and interact or react rather with other species. Also, I would like to mention, for the case of, say, an incomplete octet, like the boron example I went through, those structures are typically found as intermediates in chemical reactions. So these are the 3 exceptions that I wanted to go through in this video so that you knew that they would exist. And I hope all of this makes sense to you guys as we move forward now and start looking at the geometry and bond angles in these structures. I'll see you guys in class.